Okay, so we're going to talk about concavity and points of inflection. This is doing everything that you do with the first derivative except you're using the second derivative, and it gives you different pieces of information. So instead of telling you where a function is increasing or decreasing, it talks about concavity. So for determining concavity, you need to find the second derivative and see where it's zero and where it doesn't exist. And you break the graph into intervals and test. You're testing a point from each interval in the second derivative. So that would be where you could graph it as a shortcut and look at your second derivative. At that point, one of two things is going to happen. If the second derivative is greater than zero, then f of x is concave up. And I always think of that as it makes this sort of shape, so it's sort of happy looking. If it is less than zero, then f of x is concave down. Then it's sad-faced. And then every single place that you switch is a point of inflection. Doesn't matter how you're switching, whether you're switching from up to down or down to up, they're all points of inflection, okay? The hardest part is finding and simplifying the second derivative. So we're gonna do two of these, one of which is easy and the other of which is a little messier. Okay, so first thing you need to do is find your second derivative. So first derivative is going to be 3x squared minus 12x plus 12. Second derivative is going to be 6x minus 12. And then you do two things. You want to see where it's zero and where it doesn't exist. It's a linear function, so it always exists. So here you've got x is 2. 1, they're not really called critical points for second derivative things, but 1 point. So that means 2 intervals. So you have an interval, do your test, and now instead of telling you where it's increasing or decreasing, you're figuring out if it's concave up or concave down. So you would go from negative infinity to 2, then from 2 to infinity. And you're testing a point from each of those intervals in 6x minus 12. You could graph it. 6x minus 12 really is easy enough that, fingers crossed, you can do that with brain power. This is going to be negative, that one's going to be positive, so then you're down, up. You switched, At 2, again, the way that you switch doesn't matter, it just matters that you switched. So then you have a point of inflection at 2 comma something. Again, to get the something, you have to go into the original function, not either one of the derivatives. So if you plug 2 into that original function, you end up with 8, which is your point of inflection. Same thing, if you try to plug in 2 and it doesn't exist for some reason, then it's possible to have no point of inflection. You can have 73 points of inflection, just depends on what the function's doing. Okay? You won't ever have 73 because that would be horrifying, but it is possible. All right, one more. Okay, so this one is a square root problem. Remember, for square root problems, you need to make sure that you set a domain. So this one is going to exist for everything larger than -2, including -2. Fine. So eventually, when you set up your chart for concavity, you're going to start it at -2. So you got to find your second derivative. Here you have a product, so you have to do product rules. So you've got first derivative of second plus second derivative of first. Okay. I'm adjusting this a little bit. This is really x over 2 and the square root of x plus 2. Then I would probably take it and make common denominators so that you can just do quotient rule once to find your second derivative. So then really here, you're looking at 2x plus 4, so then you've got 3x plus 4 over 2 square root x plus 2. So then you want to find your second derivative. So you've got, bottom derivative of top. So you've got the 2 derivative of top is going to be 3, so you've got 6 minus top derivative of bottom. The 2 and the 1/2 would cancel out, and then you've got x plus 2, the negative 1/2 over bottom squared. So we've got 4 and x plus 2. Sure, so looking to clean this up. Got 6 for x plus 2 minus, this is going to be 3x plus 4 over square root of x plus 2 over 4 and x plus 2. So then you'll make common denominators again. This is why second derivatives can be tricky, because you need to really watch your algebra. So then here, you're looking at 6x plus 12, because the square roots would end up canceling each other out in terms of they would go away, and then you distribute your 6. Okay. So then you're looking at 6x minus 3x, you got 3x. 12 minus 4, so plus 8 over this one and this one, so you put them together. So there's your second derivative. Fun thing what that is. So then you want to see where it's 0. See where it doesn't exist. So here you'll set the top part equal to 0. So So then you have x is negative 8/3. And you go, that's great. No one cares. No one cares because negative 8/3 is smaller than negative 2, so it's outside the domain. So that was a work for nothing. You set the bottom equal to 0. These are the same thing. You really only have to do it once before it's pointless. And you go, that is the edge of the domain. No one cares. Still have to make the chart. You have an interval. You're testing it. You're seeing if it's concave up or down. But you only have one interval because you're going from -2 to infinity. So, same thing. You can graph it and look at it, or you can just plug in something. 0 is in the middle, so I personally would probably just plug 0 in real fast in my head. If you have no urge to do that, graph away. Not wrong, okay? One thing to keep track of is if you were graphing it, this bottom part, instead of writing x plus 2 times the square root of x plus 2, you have 1.5 of them. You could always put it in your calculator that, instead of having to put square roots all over the place. It doesn't matter, it's the same thing. So if you check it, graph it, whatever, it's going to be positive, which means you're concave up. And then you have no switching, so you have no points of inflection. That's concavity.